Hey everybody, welcome back to another calculus video. In this video, we're going to be talking about differentials. You might say, well, what's a differential? Differentials are going to be our way of rigorously using calculus to approximate quantities that would otherwise be hard to compute. So, let's kind of develop some of the theory necessary for these. We've seen that we can interpret f prime of a as the slope of the tangent line to the graph of f passing through the point a f of a. And our picture for that would be something like, have our function, f, and maybe here's our point, a, f of a, and we have our tangent line there. So the slope of this tangent line is f prime of a. Now let's notice something. Even though that tangent line only hits the graph of f right there, at least for a short region around it, it's kind of tracking pretty closely. Like maybe for x values between like here and here, right? So that little red region on the graph, even though the tangent line isn't the same as the function, it's tracking it very closely. And let me make that a little more bright so you can see it. So maybe in that region, the derivative, or rather the tangent line, is a good approximation for the graph of the function. We're going to codify that with our concept called differentials. So, more formally, the tangent line with slope f prime of a passing through the point a f of a is the best linear approximation to f near a. Right? Maybe the tangent line is not a great approximation out here, or out here, right? But near a works pretty well. Okay. And you might say, great, why do I care? Right? I would rather just work with the function itself. Most time, yes. But the actual function itself might be very complex and very difficult even for a computer to work with if you're working on a large enough scale. So, working with a linear function, which is much more computationally efficient, is an advantageous thing to do, especially when you're, as I said, you're working on these large scales. So how do we build up to this? First, let's talk about something called increments. So, definition. Let's let x be a variable. And suppose it's a variable that's changing. So let's say x goes from x sub 1 to x sub 2. Maybe moving to the left, maybe moving to the right. We don't really care, right? It's going from x sub 1 to x sub 2. Then the increment in x is defined as delta x, which, for those of you who haven't seen this symbol before, this little triangle thing is delta, Greek letter. And it's equal to x sub 2 minus x sub 1. So you can think of delta x as the change in x, the increment in x, where you ended up minus where you started. Let's compute a couple increments. All right, maybe we have x going from 3 to 2.7. So then the increment in x as x goes from 3 to 2.7 is delta x equal to, okay, we're starting at 3, ending at 2.7, so we're going to do 2.7 minus 3, and we get negative 0.3. And that's okay that the change is a negative number, right? It's just that x is going down. If it was the other way, going from 2.7 to 3, the change would be positive 0.3. Maybe another example. The increment in x as x goes from 1.8 to 4 is delta x equal to 4 minus 1.8. Again, just abiding by this formula here. And that gives us positive 2.2. So, computing increments, fairly simple, fairly quick thing to do. Now, let's define a corresponding increment in y. Let y be a function of x. As x changes from x to x plus delta x, right? Let's rearrange this thing. We get that x2 is equal to x1 plus delta x. So all we're saying here is, hey, x is incrementing up some amount, delta x, and we're going to ask what's happening to y. Well then, the corresponding change in y is going to be our increment in y. And our formula for that is going to be delta y equal to f of x plus delta x minus f of x. So the output where we ended up minus the output where we started. Okay, again, nice and simple. Except again, if f is complicated, maybe this one isn't as easy to compute. Okay. That's going to correspond to what the function is actually doing. But now, how can we use the derivative? Let's see that. Also, this should remind you of how we defined derivatives, right? F of x plus h minus f of x over h. Take a limit as h goes to 0. All that's doing is replacing an h with a delta x. Okay, so let's draw a picture for this. maybe this is our point x, and this is our point x plus delta x. So this distance here is delta x. Okay, then here corresponds to f of x, and up here corresponds to, I'm going to put it on the other side, f of x plus delta x, right? By the definition of the function f. Okay, so then this difference here is delta y. Now let's define what a differential actually is. We'll leave this picture up. What if we put on the tangent line at x f of x to this graph? So again, this is the line who has slope f prime of x. And let's again recognize this is tracking very, very closely near that point of intersection. As long as delta x is small, maybe delta x isn't that big, maybe delta x was right here, right, x plus delta x. Then this tangent line, the difference in y and the tangent line is going to, well, approximate the difference in y for the original function. Let's say that when delta x is small, we'll call it dx. So, yeah. Let's say, note, slope of tangent line at x f of x is f prime of x, or in other words, dy dx. So, for a little change, x plus dx, so we have a distance dx here. Our corresponding difference on the line is dy. And I know we've said that dy dx is not a fraction. It's still not, but this is kind of going to allow us to treat it like it is, at least in this one-dimensional sense. All right. Faffed around enough, let's formally define what a differential is. I hate the notation because it's bad and it makes people think that dy dx is a fraction, but it's the notation that your book and every other book, calculus book in the history of, well, as far as I know, has used, so we're going to just suck it up and deal with it. Definition. Let y equal f of x be differential. Then, the differential dx of the independent variable x is dx equal to delta x, right? So we're saying, hey, as long as delta x is small, so maybe our delta x was this smaller distance to begin with. So x plus delta x was here. So now That's dy. And then delta y would be ever so slightly larger. Okay, so we're going to say dx is just our delta x. So this is equal to x plus dx. And now let's define, so this is the differential dx, the differential dy of the dependent variable y is dy, which is equal to f prime of x times delta x. But because we've defined dx equal to delta x, this is going to equal f prime of x dx. You might say, okay, where are we getting that formula for dy? That seemed kind of out of the blue. Well, it's going to come from the definition of the slope of a line. Alright, so we have the point x plus delta x dy on our line. Sorry, not dy. If we say this is fx, it's fx plus dy is on our line. Which has slope dy over delta x. Why dy over delta x? Well, if we have this point f of x plus dy, x plus delta x on our line, so that point right there, and we have this point on our line, the slope is that point minus that point. So you get dy plus f of x minus f of x. So dy divided by x plus delta x minus x, which is delta x. So writing that out formally, we'd have f of x plus dy minus f of x over x plus delta x minus x. Alright, so that's our slope. And now delta y is roughly dy, right? Delta y and dy are very close. Dy would just be equal to f prime of x delta x, right? Since this is f prime of x, the slope of the line by definition is f prime of x. Alright, so hopefully that wasn't too confusing. All that we're really doing here is we're saying, hey, delta x, for a very small change, we're going to call dx, and then when that happens, delta y is very close to this thing called dy. And we define them formally like this, with this formula for dy coming from the equation of the slope of a line. Alright, so we have these differentials, and you might say, well, I still would like to know, when are these actually useful? Great question. Let's do some examples with them, and we can see that this is actually a powerful technique. Side note, this isn't something I'll ask a lot of questions on, but it is something important because it's how computers actually compute a good number of things, and you should probably know what your phone is doing when you type in square root of 32 and stuff like that. All right. So, also, quick note. dx equals delta x. dy is about delta y. Don't confuse the two. Let's let y equal x cubed. Let's find the differential dy of y. And use it to approximate delta y when x changes from, let's say, 2 to 2.01. So we have a very small change in x, only 1/100th. So maybe here it's a good idea to use the differential as an approximation. The idea of, hey, what actually is a small change, right? If you have a function that looks like this, a very small change might still correspond to a very large change. So that's not a rigorous idea, but we don't necessarily have the tools to formalize that in an introductory calculus class. So take my word, as long as this is a small enough change, and for this function, it is. All right, so in this case, y prime, aka our f prime of x, is equal to 3x squared, right? Immediately follows from the power rule. So in that case, dy is equal to 3x squared dx. So that's our differential, is just 3x squared dx. And now, to approximate delta y is about dy, which is 3 times our x squared. X in this case is 2. Why is x 2? Because that's where we are starting at. So your x is going to be your starting value. 3 times 2 squared times this dx. dx is our delta x, our change in x, which is going from 2 to 2.01, so dx is going to be 0.01. Plug that into your calculator and you get 0.12. So that's our delta y. So as x changes from 2 to 2.01, so as x undergoes a change of 0.01, y is roughly going to be undergoing a change of 0.12, right there. All right, that's all well and good. Let's see kind of another practical application of this. One of the first things that people used all this differential nonsense for was to approximate hard to compute functions like logarithms or exponentials or specifically square roots. Right? We all know that, oh, maybe it's easy to compute square root of 36, square root of 49, right? Anything that's a perfect square. And maybe things like square root of 8 aren't too bad, right? That's equal to 2 times the square root of 2. And 2 is a small enough number that we can just start computing what the square root of 2 is. But what if I get something weird under the square root sign? For example, let's say we want to approximate the square root of 37. 37 is prime, so this is about as bad of a square root that can possibly happen. How do we approximate it? Well, let's let our function y be the square root of x. We can view the square root of 37 as being a difference between the square root of 36 and 37. And we'll see that in a second. So, if y is the square root of x, it's also equal to x to the 1/2 power. By the power rule, that means that y prime is equal to 1/2 x to the negative 1/2, aka 1 divided by 2 times the square root of x by standard exponent rules. So now, dy is equal to 1 over 2 times the square root of x dx. Our change in y is roughly this. Okay, so how is that useful to us? Let's let x equal 36. Why 36? Because it's the closest perfect square to 37. Right? Something that we know how to take the square root of. I just said of twice. Goodness gracious. Alright, so we know how to take the square root of 36. We'll use our fact that we know that to approximate the square root of 37. So in this case, you know what? I'll move this on up to the other side. Want us to have plenty of space. Not because it's necessarily a long computation, but because I want more space. So, if x is 36, then the change in y between square root of 36 and square root of 37 is roughly dy when x is equal to 36 and delta x is equal to 1. And that's equal to, by our formula for dy over here, 1 divided by 2 times the square root of 36 times 1. That's 1 divided by 2 times 6, 1/12. And 1/12 would be, in decimals, 0.083 repeating. Okay, so now 0.083 is about our delta y, which is equal to the square root of 37 minus the square root of 36. That's what we've evaluated with this differential here. The difference between square root of 37 and square root of 36. So now, if we want to find square root of 37, we can just add square root of 36 on both sides. Square root of 37 is roughly square root of 36 plus 0.083 repeated. But the square root of 36 is just 6, so this is 6.083 repeating. Alright, so that would be our final answer for this question. If we approximate square root of 37 using this method, we get 6.083 repeating. Now, you might ask yourself, how close is that to the actual value of square root of 37, since this is just an approximation? Well, if you actually were to compute square root of 37, a computer would spit out 6.08276 yada yada yada, which is very, very close to this number, right? So it's off by less than 1,000. Yeah, it's off by roughly like 5 10,000ths, so 1 in 2,000, right? That's a pretty good approximation for something that wasn't a lot of work. which is why people in like the 1600s and such use methods like this to compute square roots. You might say, well, then how did we get this more sophisticated number? There's a way of repeating this process essentially over and over again, and if you keep going with it, then it gets a more precise number. But in practice, that's computationally inefficient for anybody besides a computer, so we let them do that, and we'll just say that's our best approximation. All right, so that's differentials, aka the calculus of rigorously approximating things. As I said, not super important for the overall course, but a nifty thing to know. Have a great rest of your day.